Welcome to video lecture F5. This one is on diagonalization of square matrices. I'll be your chaperone, Tom Roby. Here are the outline and objectives. Today we're going to do one of our main factorizations in linear algebra, this diagonalization factorization. And what we'll be doing is leveraging our knowledge of eigentheory and similarity to diagonalize some of the n by n matrices. And not all n by n matrices can actually be diagonalized, so we'll also want to give conditions that let us know whether an n by n matrix is diagonalizable or not. And what I mean by diagonalizable is just similar to a diagonal matrix. We've already seen why this is useful, for example, if we want to take powers of a matrix. And here's the main theorem. So a matrix, an n by n matrix, is diagonalizable. In other words, it can be written as PDP inverse for some invertible matrix P if and only if A has n linearly independent eigenvectors, which I'll call V1 through Vn. So when this happens, we get that the matrix factors as PDP inverse. So in other words, A is similar to the diagonal matrix D. The diagonal matrix here will just be the matrix of eigenvalues, where we might have the same eigenvalue more than once on the diagonal. And P will be this invertible matrix of the eigenvectors. Okay? And I'll explain the key idea in a minute, but let's first look at this example, just to keep it very concrete. If A is this 2 by 2 matrix, 1, 2, 5, 4, then it factors as 2, 1, 5, negative 1, times this diagonal matrix, 6, 0, 0, negative 1, then times the inverse of that matrix. Now you can do a couple of quick reality checks. So for example, what's the determinant of this matrix? Well, it's minus 2 minus 5, right? So negative 7. And that means that if I wanted to compute its inverse, I would have to divide every entry by negative 7, and then interchange this one and this one, and just negate the ones on the off diagonal. And so I think that's what I've done here, right? I have, if I switch this one, then I have negative 1 here and 2 here, but then I divide by minus 7, I get 1/7 and negative 2/7. On this other diagonal, I'll have negative 5 and negative 1 divided by negative 7 gives me 5/7 there and 1/7 there. So I definitely have something where it's P, P inverse, and then this diagonal matrix in the middle. And we'll come back and look at it again in a minute. But so what's the key idea? Well, writing A in this form, PDP inverse, is the same thing if I multiply on the right by P. Then I'll just get AP equals PD, right? The P inverse will cancel with the P. So that's the same thing as, those two things are just the same algebraically. Now, if I write P as column vectors, V1 through Vn, without making any assumptions about them to start with, then that's the same thing. AP equals PD is the same thing as saying A times this list of columns is equal to the list of columns to the diagonal matrix. So far so good. Next step is here, multiplying A times a bunch of times this matrix. If I know what the matrix is column by column, I can really just write that as A times V1, A times V2, as each of those individual columns. And that's something that we've seen before. It's come up. And now on the other side of the equation, when you multiply by a diagonal matrix on the right, it's easy to see that all you do is rescale each column by that corresponding diagonal entry. So that means I get lambda 1 V1, lambda 2 V2, and so on through lambda n Vn. Now, matrix multiplication doesn't commute. If you multiply on the other side by the diagonal matrix, you'd actually be rescaling the rows, not the columns. But here, that's not important here. Here, we're rescaling the columns. And so now, what does this column by column comparison give us? Well, it says that AV1 has to be equal to lambda 1 V1, AV2 equals lambda 2 V2, and so on. In other words, each of these V sub i's is the eigenvector of A corresponding to lambda sub I, or is an eigenvector of A corresponding to lambda sub I, because eigenvectors aren't unique, eigenvalues are. Okay, so this is actually the key to it, and the rest of it I can just tell you in words. So if a matrix is diagonalizable, then that means that I have this factorization where P is invertible. And if P is invertible, when I look at its columns, the columns of that matrix have to be a basis. In other words, they have to be linearly independent. Now this computation showed that those things have to be eigenvectors, and so I'll have n linearly independent eigenvectors, which is the other side of the statement. That's what I'm trying to prove. Conversely, if I have n linearly independent eigenvectors, I can define P to be that matrix. This computation, so first of all, if those are linearly independent, then they form a basis for R to the n, which means by the invertible matrix theorem that that matrix itself is invertible. Okay, so then just by this computation, we see that because they're eigenvectors, we get that A equals P dP inverse. And P inverse makes sense. Okay, so there's not a huge amount to this except unraveling a bunch of definitions and symbol pushing that are becoming quite familiar at this point. And so one more thing to take a look at here is what happens. So the point is that 2, 5 and 1, -1 should be eigenvectors corresponding to 6 and -1 respectively for this matrix. So for example, if I multiply just this first column, 2, 5, by 1, 2, 5, 4, what do I get? Well, I'll get 2 plus 10 is 12, and 12 is 6 times 2. And when I do this one, I'll get 10 plus 20, so I get 30, and 30 is 6 times 5. Okay, so 2, 5 is an eigenvector for A corresponding to 6. And you can similarly check that 1, -1 is an eigenvector for A corresponding to -1. Okay, so that's what this theorem is saying. And a corollary of this, and something that we did earlier, is that if you have a matrix that has all eigenvalues distinct, so it has n distinct eigenvalues, then it has to be diagonalizable. And you don't need to, I mean, there might be some work done in diagonalizing it, but you know it has to be diagonalizable. So this is one of those conditions that we'd like to know. And what's the proof of that? Well, we know that eigenvectors corresponding to distinct eigenvalues are linearly independent. That was something that we proved earlier. So if we have n distinct eigenvalues, then we know we have at least one eigenvector for each of those eigenvalues. They're all linearly independent. Therefore, we have n linearly independent eigenvectors. And now we can just use this statement to say that it has to be diagonalizable. Okay, so for example, this vector, what can we say about this matrix B? What can you say about its eigenvalues? Well, it has a special form, right? It's triangular, which means that the eigenvalues are just the diagonal elements, 2, -1, and 4, the eigenvalues of B. Those are all distinct. Therefore, that matrix can be diagonalized. And I'll show you a procedure in a minute for how to do it. Now let's look at this 2 by 2 matrix. What are its eigenvalues? Again, it's a triangular matrix, so we can just look on the diagonal, and we see that 2 is an eigenvalue of multiplicity 2. Okay? And so now here's something where you actually have to do a little bit of work, right? Because I know that C is so now I want to take C minus 2i and figure out how many eigenvectors, how many dimensions of eigenspace I actually have here. So when I do this, C minus 2i, I just get the matrix 0, 1, 0, 0. And what does that mean? Well, that means that x1 is free and x2 is equal to 0. So this implies that the eigenspace corresponding to the eigenvector 2 is equal to the span of x1 has to be 0 and x2 can be anything, so I can just write it as the span of 0, 1. So I have one dimension of eigenvectors for 2. I don't have 2 dimensions, and that means, and these are the only possible eigenvectors I can have, right? Because there's only one eigenvalue, and I only have 0, 1 and its multiples as the eigenvectors corresponding to 2. So therefore, this matrix can't be diagonalized because I don't have 2 linearly independent eigenvectors. I only have 1. So there is something to check, and we'll do a couple of examples in a minute that show you what can happen in general. Okay, so let's take a look at what our process is for diagonalizing matrices. This is a process that you'll need to be able to carry out. There'll be exam problems that ask you to do this kind of thing. And so the first thing is you need to find the eigenvalues lambda I, not counting multiplicities. So maybe this will involve finding the characteristic polynomial. Maybe you'll be told what some of the eigenvalues are for some other reason. Maybe it'll be a triangular matrix, and so the eigenvalues will be on the diagonal and be obvious. But the first step is to find the eigenvalues lambda I. Then, for each of these eigenspaces corresponding to the different eigenvalues, you want to figure out what the dimension of that eigenspace is. In other words, you want to figure out what the dimension is of A minus lambda I, of the null space of A minus lambda I. So that's what these E sub lambda i's are. They're just the null space of E minus lambda I. And we haven't actually proven this yet, but it turns out that the multiplicity of lambda I is at least as big as this dimension. So what can happen is that the dimension isn't big enough. And we'll see an example of that in a minute. But so you compute a basis for the eigenspace, because you're looking for as many linearly independent eigenvectors as you can find. And then once you've found that, there's nothing left to do, really. That's all the hard work. You just write the diagonal matrix as just this list of eigenvalues with multiplicity. And then the P has to be the corresponding eigenvectors. So it actually doesn't matter. You can diagonalize in more than one way. It doesn't matter which order you decide to list the V sub i's and the lambda sub i's in. They just have to correspond to each other. So V1 has to be an eigenvector for lambda 1. V2 has to be an eigenvector for lambda 2, and so on, which is what we saw in the proof of the preceding theorem. Okay? And then the steps are 3 steps, but then the 4th step that you should always do when you do any computation is to check your work afterwards. So you want to check that. And it's a pain to invert a matrix, so instead of checking that A equals PD P inverse, we just check that AP equals PD. All right, so let's look at an example concretely. So here's a matrix A. Just by looking at it, there's no way to tell what the eigenvalues are. So you need to compute the characteristic polynomial. And so for that, you're just going to compute A minus lambda I and take the determinant of that. When you do that, you end up with a cubic polynomial. And that cubic polynomial is just negative lambda cubed plus 3 lambda squared minus 4. You factor that. Hopefully, it's not too hard to factor. But if it's going to factor as integers, which is often the case, at least in the world of mathematical exam problems, then you know that the factors are going to have like be a divide negative 4, right? Because the product of all those constants is negative 4. So in this case, it turns out to be negative of lambda plus 1 times the square of lambda minus 2. What does that mean? That means that the eigenvalue 2 has multiplicity 2. If it had been lambda minus 2 cubed, it would have had multiplicity 3. Okay, and so this is the place where we're not sure whether we're going to get a full eigenspace or not. Now for the eigenvalue negative 1, I want to look at A plus I, A minus minus I. And so then I'm just adding 1 to each diagonal entry here. I end up with 9 minus 9, 6. And you can sort of see, well, the first and the last row add up to the middle row. So it's clearly going to be linearly dependent. But in fact, you end up with 1, 0, negative 2, 0, 1, negative 4, 0, 0, 0 when you do row reduction. That's what I mean by this little twiddle with the R on it. Instead of similarity, which I'll put an S on, this means row reduction, row equivalent. And so that means I have 2 pivots and 1 free variable. 1 free variable means that I'm going to get a one-dimensional eigenspace. And what is that? I can compute it explicitly, right? Because my free variable is x3. And so if I call that 1, then it turns out that x1 is going to be twice that. So that's 2. And x2 is going to be 4 times that. So that's 4. So 2, 4, 1 is a fine representative eigenvector for this eigenspace. Now, if you use a computer algebra program that doesn't care so much about whether things are integers or not, it might spit out the answer 1, 2, 1/2. That's clearly also an eigenvector. That's what Sage gave me when I computed it that way, because it's just half of this eigenvector. And if you take linear combinations or rescale eigenvectors, you always still get eigenvectors. So, but this is a fine way to write it. And the point is that I have a one-dimensional eigenspace. This is an eigenvalue of multiplicity 1, so they match. And so that's all good. Now here I've got, if I want to look at the eigenvectors corresponding to lambda equals 2, then I look at a minus 2i. I subtract 2 from each diagonal of A, and I get 6, negative 12, 3 across the diagonal. And now you can see, well, yeah, it looks like all of these rows are multiples of 1, negative 1, 1. And so when you do row reduction, you're just going to get this matrix, which has 1 pivot and 2 free variables. And so doing the usual way we compute these things, you can see that E2 can be written as the span of 1, 0, negative 1, and 0, 1, 1. Okay? So that means I have a two-dimensional eigenspace for my eigenvector, my eigenvalue of multiplicity 2. And that's good, because now I have 3 dimensions worth of eigenvectors. Right? How do I know it's 3 dimensions? Well, I constructed these two to be linearly independent. And both of these, each of these has to be, both of these are linearly independent from this, because this matrix, this corresponds to a different eigenvalue. And we know that eigenvectors corresponding to different eigenvalues are linearly independent. So that's why we have 3 linearly independent eigenvectors. We go back to our theorem that says that it means it's diagonalizable. In fact, how do we write the diagonalization? Well, here we're going to have AP equals this. And we want that to be equal to PD. So PD then is going to have to be, so what's D going to be? D is going to be, because of the order in which I've written these vectors, is going to be the diagonal of negative 1, 2, 2. Okay? But let's just write this, compute this out, and just double check what's going on. So if I compute this matrix, for example, the first column, I'll get 8 times 2 is 16, minus 24 is negative 8, plus 6 is negative 2, so I get negative 2 here. And then when I do 12, I take 12, negative 2, negative 10, 12, and dot it with 2, 4, 1. I'll get 24 minus 40 plus 12 is negative 4. And then when I do 3, negative 3, 5, I'll get 6 minus 12, negative 6 plus 5 is negative 1. So that's good, right? So I got the negative of this column, and this is the eigenvector corresponding to negative 1. Now when I do the same thing in the next column, what do I get? I'll get 8 minus 6 is 2, so that's good. I'll get 12 minus 12 is 0. And I'll get 3 minus 5 is negative 2. Okay, so that's good. That's twice that column. And then finally, in the last column, I'm just adding these two. So I get 6 and 6 is 0. Negative 6 and 6 is 0. Negative 10 plus 12 is 2. And negative 3 plus 5 is 2. And so this is equal to negative 1 times the original column. Each of these is equal to 2 times the original column, which means that this is equal to this matrix P 2, 4, 1, 1, 0, negative 1, 0, 1, 1 times negative 1, 0, 0, 0, 2, 0, 0, 0, 2, the diagonal of the eigenvalues. Okay? And so this checks, and I've diagonalized this one. Now, let's look at another example. I don't think I need to erase this. We'll see. But suppose that I've got this matrix, B. So it's a different matrix, right, than the other matrix that I had A originally. And it's easy to see, again, because by triangularity, I don't need to do a characteristic polynomial, that the eigenvalues are negative 1, 2, and 2. So the same eigenvalues that I had before. But computing the eigenvectors could be different. And so in particular, so there's a fact about these things, which is that if I have something of algebraic multiplicity, so maybe I'll write something down here. It turns out that the dimension of the eigenspace corresponding to lambda is always less than or equal to the multiplicity of lambda in the characteristic polynomial pi of lambda. So I won't bother to show that now, but it's a useful fact when you're doing these kinds of computations, because we want this to be equal so that we have enough eigenvectors, and it can't be any bigger than it. So the question is, for lambda equals 1, if we have an eigenvalue, then it has at least one eigenvector associated with it. So we know we have at least a one-dimensional eigenspace, but this says it can't be bigger than 1. Right? But now, our question is whether the two-dimensional eigenspace is big enough, and so that's the one we have to check. So we might as well check that one first and not even worry about -1 right away. Okay, so only worry about the things where you have eigenvalues of multiplicity more than 1. So we do the same thing. We look at b minus 2i. We get this matrix by subtracting 2 from everything on the diagonal. And when we do row reduction, we find that we only get one free variable, right? x1 equals 0, x2 equals 0, x3 is free. And so E2 is the span of 0, 0, 1. Okay, so I'll get one eigenvector, dimension 1 eigenspace corresponding to -1, and a dimension 1 eigenspace corresponding to 2. And so that means I only have, those are the only eigenvalues, so I can't have any other eigenvectors. So that means I only have 2. The dimension of the space of all eigenvectors is only 2, and I need it to be 3 in order to be able to diagonalize. So in this case, right, basically just by doing this computation, I can see that this one, that b is not diagonalizable. Okay, so those are the kinds of things that can happen, and you just have to be able to check. And so, of course, once I know that it's not diagonalizable, then I'm on an exam, I'm actually happier. It's less work to check that something's not diagonalizable, because now I'm done. I don't need to check my work. I don't need to construct D or P because they don't exist. I just need to quote the theorem. So I think that's it for video lecture F5 on diagonalization. Thank you again for your kind attention.